Let's continue our lesson talking about solutions, concentration, molarity, and dilutions. So we just finished talking about empirical formulas and molecular formulas. Now, once we know the formula of our compound, we can now do something with it. We can put it into solution and start doing reactions, which is what chemistry is all about. So now we're going to start getting into what chemistry actually is. So we're going to discuss solutions. A lot of what we're going to do for the remainder of the semester has to do with solutions. So we defined solutions back in chapter 1, and we said that they were homogeneous mixtures, meaning that we couldn't go in and individually pick out all the different pieces that make up that mixture, and like if we were to do something like trail mix. So solutions are homogeneous mixtures. I can't pick out the sugar that I put into my coffee. The relative amount of the component that you put into your solution is known as the concentration. So the amount of sugar you put into your coffee, we can measure that, and based off of the volume of the coffee, we can find the sugar's specific concentration in that solution. So solutions are made up of two different things, a solute and a solvent. The solute is the substance that is dissolved in the solution, and the solvent is the medium in which the solute is dissolved in. So it's whatever is doing the dissolving. What we're going to talk about this semester is going to be specific to water. Our solvent is almost always going to be water. So we have a few examples of this. Powdered drink mixes are a big one that we see in our daily life, whether that's packets of lemonade that you put into a water bottle, pre-workout that you put into a shaker bottle before you go to the gym. Those are all examples of solutes and solvents that we mix together to make a solution. Now, solutions have a new unit that we have to discuss. It's how we express that specific concentration of the solute in the solution. So this unit is called molarity, which we denote by the letter M. Capital M to be more specific. So molarity, or molar concentration, is the number of moles of solute in exactly 1 liter of solution. Exactly 1 liter of solution is very important for what we're going to use for molarity purposes from here on out. Molarity is a derived unit, meaning that its units come from other units. So we see that molarity has units of moles as well as liters. So it has quantifying units, so moles, we can count the number of moles, we can weigh the number of moles, and then we also have volume units in the liters. When we're talking about molarity, we always have to use moles and we always have to use liters when we are discussing molarity. So, and we always have to remember that the solute is going to be the moles that we use, and the solution is the total liquid volume that solution is overall. So we can calculate molarity using that expression, molarity equals moles of solute over liters of solution, because it becomes a 3-variable problem. If you know 2 of those variables, we can solve for the 3rd. So the example I have in front of us is, suppose a 355 milliliter soft drink contains 0.330 moles of sugar. Calculate the molar concentration of sugar in the drink. So, if we identify our values here, we identify our values as 355 milliliters and 0.330 moles. So we see that we have our volume unit as well as our mole unit. There's one specific thing about our volume unit that we have to take into account, and that's the 355 milliliters. Whenever we're working with molarity, it has to be in liters. So before we can plug in those numbers and solve for molarity, we have to convert from milliliters to liters, and then we can plug in our values. So we have 355 milliliters that we are going to divide by 1,000 because there are 1,000 milliliters in 1 liter. So we take 355 and divide it by 1,000 and we get 0.355 liters. Once we've done that conversion, we can now plug in our values that we have in the correct units to solve for molarity. So molarity, again, capital M, is moles of solute, which is our 0.330 moles of sugar, divided by the 0.355 liters of our total soft drink solution. So, to solve for molarity, we get 0.330 divided by 0.355. And we get a molarity of 0.929577 molar. Now we're not done because we have to take significant figures into account. So our problem here has 3 sig figs from the 355 milliliters and 3 sig figs from the 0.330 moles. So our final answer should have 3 significant figures. So that would be the 929. Now we see that this 9 has a 5 after it. Okay, so that's going to cause that 9 to round up, which will round to then 10, which brings us over to the 2. So our final molarity is 0.930 molar. And that is going to be our final concentration. Now we can go one step further and say, if we now know our concentration, so I'm just going to bring that concentration down here. Let me pull this concentration down for us. Now that we know the concentration of sugar in our soda, we now want to determine how many moles of sugar are in just one sip of that soda. So we define one sip as 10 milliliters. We know our molarity and we now want to solve for moles. So we know this, we know liters of solution, we know molarity, so now we can solve for moles. Again, if we define our variables here, we have 10 milliliters and we have our 0.930 molar. So the first thing we have to do before we can plug in is take 10 milliliters, divide it by 1,000, and we get 0.01 liters. So when we plug this into our molarity calculation, we get 0.930 molar is equal to X number of moles divided by 0.01 liters. So to solve for moles, we're going to multiply both sides by 0.01 liters. And we get 0.930 times 0.01. So we get moles is equal to 0.0093 moles. And we have 2 sig figs from our volume, 3 sig figs from our molarity, therefore we're going to use 2 sig figs for our final answer. Oops, my bad, I meant to highlight. Final answer of 0.0093 moles for our moles in 1 sip of soda. Now, we could also be asked to find the number of moles and then use that mole value and a given volume to find the concentration. That's more typical of what you would find in a lab setting because we do not always have these substances already in liquid form. Typically, we have to take a mass of that solid and then we have to dissolve it in water, and then we find the concentration depending on the mass of the compound we put in and the volume of water that we used. So we have the example here of distilled white vinegar is a solution of acetic acid in water, And 0.500 liters of vinegar solution contains 25.2 grams of acetic acid. And we want to know what the concentration of the acetic acid solution is in units of molarity. So we have to first, let's write out our plan. First, we have to determine the moles of acetic acid. And then once we have the moles of acetic acid, we have to then find the molarity. So to find moles of acetic acid, we have to first find the molar mass of acetic acid. So we take our formula of acetic acid, C2H4O2. We do 2 times the mass of carbon plus 4 times the mass of hydrogen plus 2 times the mass of oxygen. So we get parenthesis 2 times 12.01 plus 2 times 1.01 plus 2 times 16.00. Oops. 0.00, there we go. Okay, and we get a molar mass. Oops, I have the wrong thing there. Wrong mass of hydrogen. 4, there we go. So we get 60.06 grams per mole. So that's our molar mass of acetic acid. Once we have the molar mass, we can take the 25.2 grams of acetic acid and divide it by its molar mass to get the molar value. So we have 25.2 divided by 60.06. That is equal to 0.41958 moles. Now, because moles is not our final answer, we are not going to round to significant figures yet. We are going to wait until the very end of the problem. So, here's our mole value. Here's our volume value, 0.500 liters of vinegar. So to find the molarity, so for step 2, the molarity is now just going to be our mole value that we found for 1958 divided by our volume that was given in the problem, which is already in liters. So we're just going to take our answer and we're going to divide by 0.500. And we get that the molarity is equal to 0.839 molar. With significant figures, 3 sig figs in our final answer because of our mass and our volume. So here we just showed how we take a mass, convert it to moles, use that mole value and the given volume to find the molarity. Now you could do this as well if you were given the mass of the compound as well as the molarity and you needed to find the volume. You could do that as well, okay? Because really what it is we're just taking a 3-variable problem. If we know 2 of those variables, whatever variables they are, we can find the third. If we have molarity in moles, we can find liters. If we have liters in molarity, we can find moles. If we have moles and liters, we can find molarity. So there's many different ways that we can solve these types of problems. Next up, I want to talk about what we then do with these solutions. After we make them and we find their concentrations, there's one additional thing that we can do, and that's diluting them. So the process of dilution is where we take the concentration of a solution and we decrease it by adding more solvent. So think of it like when you were a kid making Kool-Aid. You put your sugar mix into your pitcher, you added some water and mixed it up a little bit, and maybe you didn't add enough water. You tried to drink it and it was really, really sweet. And if it was cherry or fruit punch flavored, it was probably really, really red, okay? Then what you had to do is you had to add more water in order to dilute the solution more so you could actually drink it, so it actually tasted good. That's an example of a dilution, where we took a concentrated solution of Kool-Aid, okay? We added more solvent, we added more water to dilute the solution, and we decreased that concentration. We had a lesser concentration of that Kool-Aid mix compared to our volume of water. Now, we didn't take away any of that Kool-Aid mix. We didn't add any more. We're not changing the number of moles of our compound that are in that solution. We are just adding more solvent so that in our denominator, in our molarity calculation, our denominator, that value for volume is now increasing. If our moles stay the same and our volume increases, that automatically means that our molarity is going to decrease. So in a dilution, as the volume increases, the concentration is going to decrease. So we can use a mathematical relationship to determine the volumes and the concentrations that are either needed or what we are going to end up with in our final solution by using the relationship shown here. M1V1 equals M2V2, where M stands for concentration and V stands for volume. Again, the only thing that's changing in a dilution is the volume and the concentration. We're not changing the number of moles when we are doing the dilution. So the relationship is only between the concentration, the molarity, and the volume of the solution. So the number 1 that you see, this is our initial, and 2 is going to be our final. The initial values before we diluted and the final values after we diluted. So another way that we can express our M1V1 equals M2V2 expression is by writing it as MIVI equals MFVF, where I and F stand for initial and final. Okay, so just like our last relationship, this becomes a 4-variable problem where you know 3 of the variables and you solve for the 4th. So you will know the initial concentration and the initial volume and the final volume, and you're solving for the final concentration. Or you know the final concentration and the final volume and the initial concentration, and you're finding the initial volume that you need to use. Okay? It just becomes a 4-variable problem where you know 3 and you solve for the 4th. So let's look at an example. If 0.850 liters of a 5.00 molar solution of copper nitrate is diluted to a final volume of 1.80 liters by the addition of water, what is the molarity of the diluted solution? So I think the hardest part with dilution problems is the wording of the problems that we see, because we see multiple molarities or we see multiple volumes and we don't know which is which. So we can go by the golden rule that when we are looking at a dilution, since we are increasing our volume, by the definition of a dilution, we're increasing our volume, V1 is always going to be smaller than V2. By that same reasoning, M1 is always going to be larger than M2, because by increasing the volume, we are then decreasing the molarity. So as V2 increases, M2 has to decrease. So a good way to figure out what's 1, what's 2, what belongs where is to look at those values and how they compare. You can also look at how the problem is worded. So if I want to go and define my M1, my V1, my M2, and my V2, we read through the problem, and it says, if 0.850 liters of a 5.00 molar solution of copper nitrate is diluted. So we are saying we are taking that volume of that concentration and we are diluting it. That means that 0.850 liters is going to be our V1 and 5.00 molar is going to be our M1. Okay? Then it says it is diluted to a final volume. Final volume, that tells us V2 is going to be 1.80 liters. That corresponds with our relationship of V1 and V2 because V1 is smaller than V2. We see that. So we have 3 of our variables. Now we just set them up and we solve for M2. That's what we don't know. We want to know what the final molarity, what the molarity of the diluted solution is. So we just plug everything in. 5.00 molar times 0.850 liters is equal to M2, whatever that is, times 1.80 liters. So we're going to divide both sides by 1.80 liters, and we are going to get M2. So we can take 5.00 times 0.850, divide that by 1.8, 1.8, can't type today, 1.80, and we're going to get that our final concentration is 2.36 molar with 3 sig figs based off of the numbers in our problem. So here's our final answer. And that also falls into what we see for our relationship between M1 and M2. M1 is 5.00 and M2 is 2.36. So we've successfully decreased our concentration. Now, how do molarity calculations and dilution calculations work together? Well, we could see that we don't know, let's say, our initial concentration, so you could be asked to find that initial concentration using a molarity calculation of moles over liters. And then you could be asked to take that concentration and dilute it to some volume, to some concentration, and find the missing variables from there. So they kind of work stepwise, where we take molarity calculations first and then dilution calculations second, and then we can go from there. And remember, whenever we're given molarity, there is also always a way to find moles and grams because we know the substance. If we know the substance, we know its molar mass. If we know its molar mass, we can transfer and convert between grams and moles and grams. If we know moles, we also know molecules by Avogadro's number. So there's many different ways that you could see these problems worked in with other topics that we've discussed in the past, back in chapter 2, with molar mass and Avogadro's number. So as you go and start your homework on these problems, you'll see a lot of calculations working on molarities and using the molarity calculation, conversions that you need to do to make sure everything's in the right units, as well as some additional practice with dilutions and solving for M1, M2, V1, V2, depending on the situation.